Okay, before getting started, I made a typo on this page. That was supposed to say x minus 2 right here. Alright. I'm just trying to add a little bit more to rational functions. And partial fractions is something that happens in calculus, probably Calc 2 and beyond. But it's certainly an interesting lesson. And maybe before I get started on this, I'm just going to investigate, for instance, and I've kind of messed around with this already, is a very simple value like 7/12. What I'm trying to get you to realize is that you can rewrite 7/12 as the sum of something else, like 3 plus 4 over 12. Which then you could rewrite as 3/12 plus 4/12, which then you could reduce that to be 1/4 plus 1/3. And here's the thing, is most students are very familiar starting here with the 1/4 and 1/3 and going backwards here to here to here and getting that final answer. But what I'm trying to get you to realize is that sometimes in math, it's better to go the other way. And it's sort of beyond the scope to explain why it's better. It's just something that we're going to investigate. So again, make sure that you fix my typo for this very first example. And as a reminder, you probably did this. You actually did this in section 1, 3.1, where you got the same denominator, x minus 3, x. Oops, I was supposed to say plus 2. There, I fix it, and I don't even fix it correctly. But in order to get that same denominator, you had to multiply the left side by x plus 2. So as I distribute that 2 in there, that's 2x plus 4. And then I need to multiply the right fraction by x minus 3. X minus 3. So distribute that, and you get minus x plus 3. And then when I simplify that, now earlier I didn't have you FOIL out that denominator, but I'm going to go ahead and do that now. And on top you end up with 2x minus x is 1x plus 7. And what you notice is it equals that. So here's where we're heading with this. Is if you notice the denominator, what you do is you factor the denominator. So if you were to factor that, your two terms would be x minus 3 and x plus 2. Well, I'm just going to rewrite this for a second. How about I rewrite in factor terms, x minus 3, x plus 2. And I leave that numerator alone, x plus 7. Now, I don't know what the numerators are, so I'm going to put an A here, capital A, because I don't know what that number is, and a capital B here, because I don't know what that number is either. And the whole premise is to multiply everything by this denominator. Because if I multiply everything by this denominator, x minus 3, x plus 2, it'll cancel out that, so I'm just left with x plus 7 on the left side. On the right side, the x minus 3 will cancel out with the x minus 3 because I'm multiplying everything by it, but I need to multiply the top by x plus 2 then. And same thing with this value, the x plus 2 will cancel out, but not the x minus 3. So then what I have is ax plus 2a plus bx minus 3b is equal to this term. So let me just rewrite it for a second. I'm going to do two things. I'm going to get my ax and my bx together. And let me put parentheses around it. And I'm going to have 2a minus 3b put together. Just like that. I should have gave myself a little bit more room. And what I can do is I can factor out an x. So what I know is a plus b added together must be equal to 1 x. And then I know that this term, 2a minus 3b, 2a minus 3b must equal this linear term, which is 7. I guess I should explain this a little bit better. Because if this is going to be an identity, the linear part, the constant, must be equal to the constant over here, and the coefficient must be equal to the coefficient over here. So the sum of a and b need to add to be 1, and the constant 2a minus 3b must be equal to 7. So now it's a system of equations where I could just double. So 2, I'm doubling this by the way, 2a plus 2b. And the reason why I'm doing that is now I could subtract off that term. So I have 5 is equal to negative 5b. And from there I can say, okay, well, b needs to equal negative 1. And that's exactly what happened. And also, back to the statement that a plus b must equal 1. Well, if b equals negative 1, a plus negative 1 must equal 1. So add 1 over, and a must equal 2. And that's exactly what was stated over here. So what we're doing is working backwards in this section from what you're probably familiar with and trying to figure out what that answer is. Now notice that this is a step-by-step, I know it's blurry, I'm sorry it's blurry, on how to do the decomposition. What you want to do is make sure that you have a proper fraction. That means the degree in the numerator is greater than, you want the degree in the numerator to be less than. So what do is you divide it using long division to make it a proper fraction. And then you factor the denominator, that's what I did earlier. And then try to reduce it. And then notice how you write out your terms, but it gets a little bit trickier when you have quadratic terms, and that's actually the first example we have. So the example I did up here had linear terms, and then the factor down here, we haven't gotten to quadratic yet, but that's actually on the next slide. Yeah, so as we look at this, you see how the degree in the numerator is smaller. So we can just sort of jump into the problem. It is already in proper form. So what you want to do is then factor the denominator. So as you factor that denominator, we're at x and then x squared plus 4. So I hope you're okay. I'm going to go ahead and rewrite x cubed plus 4x is x times x squared plus 4, because I'm going to split that up as x and x squared plus 4. Let me switch back to black. That 3x squared plus 4x plus 4 is still in the numerator. Okay, I just got it from right there. So the way we set this up is this is a linear term, so we just need an a on top. But this is a quadratic term, it's squared, so we need bx plus c. So now what I'm going to do is multiply everything by this denominator. So this is going to cancel out, and on the left side I just have 3x squared plus 4x plus 4. Now this x will cancel out with the x, but you still have x squared plus 4. And if it helps, go ahead and FOIL that. Ax squared plus 4a. Now in this fraction, the x squared plus 4 will cancel, but you need to multiply by that x. So we have bx squared plus cx. I distributed that in. So what do we have? On the left side, we have 2x squared. So I can put those together as a plus b x squared. We have, I like to write cx next, and then plus 4a. So let me highlight what we have. I feel like I'm doing better explaining this than the first example. Is the 3 was the x squared term. So 3 has to equal a plus b. The 4 is with the x term. Well, that's just c. So there we have one of our answers. I switched to purple. That c must equal 4. And then our constant in the problem, choose this color, is 4a, which has to equal this 4. Oh, that's helpful, because if 4 equals 4a, write it small, then divide both sides by 4, and a must equal 1. Okay, well, if a equals 1, and a plus b equals 3, that means that 1 plus b needs to equal 3, so b must equal 2. So going back to our problem, way up here, we have now established that this is equal to a, which was 1 over x, plus b right here was 2x, c was 4, all over x squared plus 4. And this is your final answer for the decomposition of that function. I'm going to stop the video right here because I only have 2 more examples to show you anyway. And I guess work through them there.